Hi ladies, today we're going to talk about powers of monomials. Let's go ahead and start off with an exercise where we are looking at some squares and trying to calculate their areas. Let's see what happens. Okay, so I know my squares on this tablet are not perfect, but imagine that they were. So here we have square A, and it has one side with a length of little a cubed, and of course the other side would be little a cubed as well. And we have another square whose sides are equivalent to b to the fourth. We have another square C. We have c to the fifth. And another square D. Let's just say d to the 10th are the dimensions here. So we have 4 different squares, each with different lengths. What I would like us to do is to go ahead and kind of make a little table looking at each of these different squares and writing down their areas. So I know the area is equal to base times height because we're looking at a parallelogram. In a square, of course, the base and the height are equal. So let's go ahead and say for A, it would be a cubed times a cubed. Okay. B would be b to the fourth times b to the fourth. Then we'd have c to the fifth times c to the fifth, and d to the 10th times d to the 10th. Now we're going to work with this just a little bit. I do know that we can simplify these. We've talked about the product of powers property, and we're also going to relate this to another way to write it with exponents. So let's go ahead and just recognize that when I say a cubed times a cubed, I could also say that I'm taking a cubed and that I'm multiplying it by itself twice. With b to the fourth, I'm doing the same thing. I'm taking b to the fourth power. Sorry, I don't like the way these look. So I have a cubed times a cubed, so really that's a cubed squared. B to the fourth times b to the fourth, which is really like b to the fourth squared, and c to the fifth times c to the fifth, which is like c to the fifth squared. Same thing with d to the 10th. I'm taking d to the 10th, multiplying it by itself, so I'm squaring it. We know that a cubed times a cubed could also equal a to the 9th, except that it doesn't. Sorry. It equals a to the 6th, because 3 plus 3 is 6. We also know that b to the 4th times b to the 4th is equal to b to the 8th, because 4 plus 4 is 8. c to the 5th times c to the 5th will give you c to the 10th, because 5 plus 5 is 10. And the last one, d to the 10th times d to the 10th, would equal d to the 20th. Now, I just want to point out that all of these are equal. They mean the same thing. They're each written a different way, but they mean the same thing. And ultimately, this is the most simplified. The property we're going to explore today deals with powers of a power, and that's why we took the time to recognize what was happening with this repeated multiplication and the fact that we could rewrite it using another exponent. So let's go ahead and just jot down that property. The power of power of powers property states that when we have a power to a power, we can actually multiply the exponents together to get our simplified exponent. So a cubed squared is really a to the 6th, or 3 times 2. b to the 4th squared is really b to the 8th, or 4 times 2, giving you the 8. c to the 5th squared is 5 times 2 is 10, c to the 10th, and d to the 10th squared is d to the 20th, because 10 times 2 happens to equal 20. So in other words, if we have a to the m, which happens to be to the n, we can simplify this to a to the m times n. Let's take a look at some examples. So for example, if I have 9 to the 6th squared, just to recognize what's happening here, what we are really doing is 9 to the 6th times 9 to the 6th. And again, we can use the other property that we've learned to, add 6 and 6 together. Or with this new property, we can recognize that a power to a power allows us to multiply these exponents and say 9 to the 6 times 2, or 12. Okay, so everything's related. We can also look at something like this. Maybe I have q to the 10th to the 5th power. And again, I would prefer not to have to write this out as repeated multiplication, q to the 10th times q to the 10th times q to the 10th, and so on. So I can use our new property and recognize that I am taking q to the 10th and multiplying it by itself 5 times. So in essence, I have q to the 50th power. We can do this with negative exponents as well. So let's say we had 2 cubed to the negative second. Okay, the same rules apply, and this is kind of fun to work with. I can go ahead and say that this is equal to 2 to the 3rd times negative 2, and it equals 2 to the negative 6th. And I can go ahead and prove it. This is cool. So I have 2 cubed times 2 cubed, and all of this is under 1, because with our negative exponent, that's what we would do. We would rewrite this as 1 over 2 cubed to the 2nd power. And instead of writing it like this, I could use the fact that, this is 2 times 2 times 2, this is 2 times 2 times 2. Okay, multiplying it together, I have 6 of them, or 3 plus 3 to get the 6. Okay, and I can say it's 1 over 2 to the 6th power. And if I was to rewrite that using a negative exponent, I would say it's equal to 2 to the negative 6th. So all of these properties are intertwined. And for an example like this, I would accept either answer. You could say that it is, I lost my thing there, 2 to the negative 6th, or you could say that it's 1 over 2 to the 6th. Either answer would be correct. Okay. What's neat is that we can also do this if the base is more than just a single number or a single variable. So let's take a look at some of those types of examples. Let me flip my page here. So let's say we had something like this. I have 2x cubed to the 5th power. Okay, well, what does this look like? Remember, you can always derive the property. You can always write this out as repeated multiplication to figure out how many x's you end up having and how many 2's you end up having. So even though we use these properties to make the math a little bit more efficient, we can always go back and factor everything out. And let's take a look to see what this looks like when we factor this out. Basically, I'm using this entire monomial as my base, and I'm multiplying it by itself 5 times. So I'm taking 2x cubed times 2x cubed times 2x cubed, 1, 2, 3, 4. I'm going to go over my line here. Sorry. Times 2x cubed. And if I use the associative and commutative properties of multiplication, I can recognize that 2 is being multiplied by itself 5 times. 2 is not being cubed, only the x is being cubed. So that's something important to point out, that with the property, with PEMDAS, the order of operations, x is being cubed and then 2 is being multiplied by that. So 2 is being multiplied by itself 5 times. 1, 2, 3, 4, 5. And then x cubed is being multiplied by itself 5 times. 1, 2, 3, 4, and 5. And we can simplify this using exponents. We can recognize that, aha, I have 2 to the 5th power times x cubed to the what? 1, 2, 3, 4, 5, also to the 5th power. And we can simplify this further by using the property we just explored, by saying 3 times 5 and getting a new exponent of 15. So our final answer here, simplified, without actually figuring out 2 to the 5th, sorry, writing it with exponents I should say, is 2 to the 5th times x to the 15th. Now, that takes a long time to write out. And what if you had to the 10th power or something? You wouldn't want to have to do that all the time. So again, what's the connection from here to here? What's that connection? Well, it looks like we essentially distributed the exponent. We gave the exponent to the 2, and we gave the exponent to the x cubed. And this is different from the distributive property because the distributive property works with multiplication over a sum or a difference. So there is a difference here, but you do want to see what's happening. And this is called the power of a product property. So power of a product property. And this basically states that whenever you have a product, like up here we had 2 times x cubed, so for example, I don't know, 8 times b to the m power, this is equal to a to the m times b to the m. Okay, that is equal. Let's take a look at another example. Let's say we had 5r to the 7th squared. This is equal to 5 squared times r to the 7th squared, which is equal, and let's go ahead and do 5 times 5. 25 r to the 7 times 2 would give you 14. Okay, so this is the most simplified we can get here. Okay, let's look at another one. This one's fun. 2x to the 6th, y cubed to the 4th. This is all just manipulation, and it's getting you used to this kind of manipulation. So we're just doing a lot of practice. So here I have 3 terms being multiplied together. I have 2 times x to the 6th times y cubed. So again, I'm going to give this exponent of 4 to each of the values on the inside of the parentheses, and this is equal to 2 to the 4th times x to the 6th to the 4th times y cubed to the 4th power. And this can be simplified further. Let's go ahead and write that out. 2 times 2 times 2 times 2, just remember that. You get 4 times 4, that is 16. And then x to the 6th to the 4th, I can multiply 6 times 4 to get x to the 24th. Y cubed to the 4th power would give me y to the 12th. So 16x to the 24th, y to the 12th. This is the most simplified version. And again, it works really nicely not to have to write out this entire expression, because I would have ultimately 24 x's and 12 y's. It would take up a lot of space on your paper. We can relate this property to volume. Just as a reminder, to find the volume of a cube or any rectangular prism, I should say, volume is equal to length times width times height. Okay, so let me flip my page here so I have more space. Let's say you have something like this. You have a cube, and I know that this expression, 2xy to the 5th, is equal to the length, the width, and the height. And the volume of the cube means I need to multiply all of these together. So the volume would be 2xy to the 5th cubed. I can simplify this by distributing my exponent. I get 2 cubed times x cubed times y to the 5th cubed. When I simplify 2 times 2 times 2, I get 8x cubed, and then y to the 5th cubed gives me y to the 15th. So this expression here would represent the volume of this particular cube. And if I knew what x and y happened to be, I could substitute those in right here and get the volume right away. Just as a reminder, volume is always in cubic units. Area is in square units. Thank you very much, and we'll practice this tomorrow in class.